Good afternoon, everyone. We'll get started here. I'm really excited to see the attendance here. I never thought I'd see a seminar that would create actually a fire safety hazard. But for today's speaker, it's Dr. Art Kuo, who's going to talk about Much Ado About Induced Accelerations. I've always wanted to do this type of introduction, and I can't find a more appropriate person to do it for. Dr. Art Kuo is a person who needs no introduction. Plus, Art didn't want one.
Thank you, Mike. The number one question I've gotten in the 21st century is, what is going on? This is a technique called muscle-induced accelerations that's sort of taken the biomechanics world, as a storm. And muscle-induced acceleration analysis has led to some rather puzzling results, such as during gait, the soleus produces negative upward power. The soleus and gastrocnemius, those are your calf muscles, produce opposite energetic effects on the leg and trunk, even though they're both part of the calf and they are different muscles, but some people would expect them to act somewhat similarly. So over the years, I've gotten lots of questions about how can this be? Let me just use this highlight to show that that's the area that we're talking about where the soleus is contributing negative power to upward acceleration of the trunk. So people have been wondering about this. Another example is during pedaling. These arrows show you the induced reaction forces, or actually the induced forces on the pedal from different muscles: gastrocnemius, soleus, vasti, gluteus maximus. You can't see here, but it's a really tiny arrow there. And the interest is, how do we produce tangential forces along the direction of the crank? And the answer is that the gastroc and soleus produce by far the biggest forces. If you add them together, they produce a force like this, much more than the vasti and the gluteus maximus. And people have been asking me, well, how can this be? And we can certainly observe, if you look at cyclists' legs, that they definitely do have big calf muscles. But you might notice that they have even bigger quads. And then we might ask, is the training there incorrect? Because obviously, according to this, shouldn't you focus really on the gastroc and the soleus rather than the quads? Another example of muscle-induced acceleration analysis is that you can break down the contributions of the different muscles to the ground reaction forces. And the result of that is that the rector spinae, your spinal muscles, actually contribute negatively to upward acceleration of the center of mass. And that also is kind of puzzling. You could do the same thing with other muscles. This is a analysis of the tibialis anterior, which shows that it accelerates the body downward. Again, somewhat puzzling. Another one is the conclusion that the majority of mechanical work performed during locomotion is support against gravity and forward propulsion. That's kind of puzzling because both should be zero. If you're walking at steady speed on level terrain, there's zero net work done against gravity, and there's zero work done for propulsion. So here's a little bit of history of muscle-induced acceleration analysis. This is only a partial list of papers, but a lot of publications, you could say mostly in the 21st century, and these have had quite a lot of impact in biomechanics. And in fact, when I said this is the number one question I get, I should actually say this is the number one question I get about papers that I had nothing to do with. because it's actually pretty rare that someone will ask me repeatedly, people will ask me repeatedly, what do you think of this other paper? Why you ask me? But those of you who are familiar with the field will know that this has been quite influential, incredibly well-cited work. There have, however, been some contrary views. Maybe a few people to point out. Andy Ruina is a long-time colleague of mine. Toon Vandenboer is a beloved former member of the Human Performance Lab right here. George Chen was at Stanford. I want to point out Andy Ruina gave a technical talk at World Congress of Biomechanics that was a contrary view, and then this is a URL that will get to it. You may be wondering, why would people be asking me questions about induced accelerations? And that's because I play some role in this. I wrote what I would say are some neutral papers about things related to induced accelerations. And then in that sense, people who know me might have some expectation that I would have something to say about this. Why are we doing this now? Well, one reason why we're giving this talk now is just because we were missing a seminar speaker for today. And so I'm just pinch hitting, and I offered to be available on short notice. But I think a more important recent development is that over the years, we actually have had discussions. Most of these people on the right here have had discussions because people encouraged us, please write a paper to explain this because we don't understand how they get these results. It's very complicated analysis, or it seems, and then people don't know how to evaluate it. They tend to believe that because the analysis is complex, that it's just something that's beyond them, but they don't understand the conclusions. So we've had discussions over the years about writing a paper about it, and in fact, we've had some letters to the editor and things like that, but not too much in the way of things that people can really look at to understand it. A variety of reasons for that. One of them is just, it's not that much fun to write just a paper against a certain method. And also, there's some concern about hurting people's feelings. But a very recent development, Brent Edwards showed me that Steve Collins unleashed a Twitter storm last semester. When was that? Was that November or something?
Yeah, it was last fall.
Okay, sometime in the fall. And if there were any feelings left to be hurt, they're gone. So Steve was not, or Steve is in general, not generally a particularly delicate person. And so I think that's sort of made it a topical thing. Also, Mike Asmussen was polling me last fall because he actually found, what did you find?
Through Ruina's
Oh, okay.
link, there's a post-art slide.
Okay, you found this, and then, actually I thought I had, okay. I actually gave a tutorial on induced accelerations, which I would say was more neutrally oriented. And Mike saw the link to that from Andy's talk. And so Mike was asking me, is there any record of that talk? And the answer is no. And we thought it might be fun to just do a seminar as a chance to stream it and record it. And this is going to be today, what we call Much Ado About Induced Accelerations, is a rehashing of this. I've updated the slides a little bit, and also the slant is not as neutral as before. And also, this is to be filled in, but my hope is that after we record this, we'll have a video, and we can put it on YouTube, and then also with that, I can package the slides so that that will be available to anybody, so that just so there's some information out there for people who are curious. The talk at World Congress, I would say, is a very technical talk, and I think it's quite good. What I'm hoping to do is a simpler version of that. And what I hope to achieve is I hope to help us gain an intuitive analysis of muscle-induced acceleration analysis, learn about the controversies a bit, how to use simple models to think about things, and then I don't want to just tell you the answer, this is right or wrong, but really the goal is to help people gain an ability to read the literature and to make their own decisions about what to think of it. And so here's what we're going to do. We'll talk about intuitive induced accelerations. We're going to do a tiny bit of math, but actually that's not the focus. The math we'll put up just so that there's a connection between what we're talking about in a hand-wavy manner, and people can look up later in the math how that actually makes sense. We'll do a couple of quick studies of pedaling, throwing a ball, and talk a little bit about gait in terms of induced accelerations, and then we'll do a little discussion. This is also the tutorial that I gave, and also what I hope to do today is interactive, and so we'll pause at times to talk about things. Okay, so the first thing is induced accelerations. What are they? This math is going to be over in 3 minutes, but I'm just going to provide the basis because that's what's used in all of the analyses. What you see here are the equations of motion for the body, and the terms of interest are theta, which you could say are a bunch of joint angles, and it's a vector, so you have basically every joint angle of interest in the body could be included in there. And then the F is a list of all the muscle forces, and there's a relationship, of course, between the muscle forces and the accelerations of the body. M, V, and G are just other terms that include things like masses of different parts of the body, moment arms, lengths of body segments. We have names for all of these things. I'm sure you've heard of, say, centripetal and Coriolis terms. We can solve for the accelerations. Usually that's the mystery, because accelerations are what happens imminently given the current state of the body, which would be the positions and velocities of things. So that's the information you know now. What you're interested in is what's going to happen next. That would be the accelerations. So we can just solve for the accelerations, and there's a bunch of stuff we can throw away because the centripetal forces are sometimes meaningful, but they're usually quite small. And then even smaller are the Coriolis forces. Coriolis forces matter more in things like gyroscopes or rockets, but on Earth, for humans producing their own motion, Coriolis forces are really small. Maybe one exception is for divers who are doing a lot of flipping. Maybe the Coriolis forces matter for them. Okay, so we can throw that away. Gravity, I think most people have an idea of what that does. And so this R matrix is a bunch of moment arms for the muscles. Those can be measured quite accurately, but for our purposes, you can just kind of guess them. You can look at your patella and say, well, what do you think the moment arm of the quads are? Muscle-induced acceleration analysis is concerned with inertial coupling. And that comes from the mass matrix, which is this big M here. And okay, so that was the math. We can flush all of that. Here's just an easy way to think about it. If you sort of let your wrist be free, and then you sort of wave your forearm around, notice that the hand is going to move even though I'm not producing any muscle forces or trying not to produce any muscle forces about the wrist. So that is what we mean by inertial coupling. You move one thing, but it has an effect on another. That's all inside this mass matrix. Or I should say the mass matrix and some moment arms. Okay, so that's inertial coupling. Oh, I lied. I said all the math is gone, but I forgot I actually have one more minute of math. You have the muscle forces. You can condense everything into a matrix. And one way to think of a matrix is you have a whole bunch of columns in a matrix, and then you're multiplying those columns against muscle force 1, 2, etc. And one way to think of that is it's the same as taking each of these columns, which is a vector of accelerations, acceleration-like things, and multiplying by the individual forces. And that means that you can look at the effect of any individual muscle force, well, I just realized these should be numbered 1, 2, 3, but the idea is that, say, muscle 1, if you were to activate it, you would know what the accelerations that result from that muscle alone, and those add with all the others to produce the overall motion. So the lesson is that accelerations are linear sum of the effects of individual muscles. Linear means that we can break things apart and we can look at each muscle's effect individually, and that sounds like a fun and useful thing to do. Same thing goes for reaction forces, hence the ability to study contributions of muscles to ground reaction force or pedal reaction force. And so we can examine each muscle individually, right? That's the idea of muscle-induced accelerations. Okay, let's do this again with no math, but just some drawings. Let's say that we have a body segment and then a hinge joint, and we're just applying a torque. That's, of course, going to induce a rotation and a translation of the center of mass. So it's going to move this way. Everything is moving in one direction here. If you're interested, here's just a key. I'll try to be consistent with this. Of anything that's a torque or force, the arrow will look like this. And then if we're talking about kinematics, I'll use arrows that look like this. And hopefully that will be consistent. Okay, so this is a tutorial, right? So we're going to do a quick exercise. Let's start with something floating in space. Or you could say you're looking down on an air table, and this is just something that's floating freely. There's no gravity that you have to worry about. It's just sitting there. And what we're going to do is we're going to whack it with an impulsive force. And we want to ask you guys, we're going to actually take a break for a minute, and we're going to ask you guys to describe or talk to your neighbor, please. Discuss with your neighbor, what is the rotation that you expect to cause from this force? That's pretty easy. What do you expect to happen to the center of mass as far as translation? And then what's going to happen to this point here? It's not attached to the ground or anything, but we have this free-floating thing. Do I have a prop? We're in space. This is floating freely. We're going to whack this, and we're just going to ask you to discuss with your neighbor what's going to happen to the rotation, translation of the center mass, and the motion of the bottommost point of this right after we whack it. And so let's take a minute to just have a little conversation with your neighbor, and I'm going to wander around and listen in on you. I'm just eavesdropping.
Is all the mass in the middle?
It is a rigid body, so it has a center mass, but it also has a moment of inertia. And what happens to that bottommost point?
So I think that it should not translate. We're discussing whether this will translate forward, or will this be, this point will move at equal opposite rotation, and what will this point will apply.
Okay. let's recap because I think I already overheard some good answers. Okay, this is what Sandro Nig said with his pair of glasses. Easily, we can say that we're going to have that point is going to move in the direction that we applied the force. And we're going to have a rotation clockwise. Of course, the center of mass, F equals ma. So the center of mass has to translate also in the forward direction. But slightly trickier is what's going to happen to this point. And actually, this point is going to move backwards. Is this point going to move backwards as fast as the point on top moves forward? No. But it will move backwards, but more slowly than the top arrow. There's also a point that, at least for that instant, there's also a point that's not going to move. So it's going to have zero velocity, at least for the really quick instant after we whack this. Does anybody know what we call this thing? Yeah, center of percussion. And you know, a way to think about it is they say in baseball that the sweet spot on the bat is very close to the center of percussion. And then the consequence of not hitting the ball at the sweet spot is that you may feel a sting at your hand. And that's because of essentially you would like the end of the bat where you're gripping not to experience an acceleration when you hit the ball. Okay, so what's the takeaway? Forces generally induce rotation and translation. And you could say overall, it's very intuitive. Everything acts the way you want to. But also, you can have some things go in the opposite direction to the force you apply. That's not really that strange, though. And in fact, overall, we do expect the everything to be translating. You know, the overall mass has to move to the right. Here are some details, which we're not going to go over, but it's just for reference that you can calculate all of this. Now let's, remember we had our body floating in space. Now we want to not float in space. Let's attach our body to a hinge joint. And let's just talk about something else that happens. We have gravity. Gravity, of course, is going to induce rotation and a translation of the center of mass. It's going to move this way. And then, and I said here, acceleration from gravity will not be very high. And why is that? And we can break this apart. Oh, actually, let me just answer that. Sorry. The reason why it's not going to be very high is because gravity is acting on this, but the acceleration you're going to experience has something to do with the moment arm of gravity with respect to your rotation point. And that I've drawn this purposefully to make that moment arm low. Okay, but we can also do a free body diagram, and that's what comes next. Is let's just think about applying a torque in this direction, where obviously we're going to get a translation and we're going to get a rotation. And we've already talked about that point at the top. We do expect it to translate a lot. So this is the velocity that you could say comes from applying an impulse about this joint. And then you have an expectation that the center mass is also going to move in the same direction, but not as fast. And the line here is just to indicate that the further away you are along this segment from the pivot point, the higher the velocity. Or you could also say the higher the acceleration given a torque. And then that's because of a term that you see in the kinematics called alpha cross r, angular acceleration cross product with the moment arm. We can also think about what happens for a bigger segment. So here I've just blown everything up. This is bigger and heavier. And one expectation, I'm going to sort of take similar points, similar distance away. And what I'm trying to illustrate here is that you get the same arrows but shorter. and they're shorter because this thing is heavier. So you're going to get smaller accelerations. Okay, so it's slower due to its mass. Okay, so translation and rotational acceleration scale inversely with mass. I think everyone knows that. And now we can also talk about the effect on constraint forces. And this is really so that we understand how the same idea of induced accelerations applies to, basically induced constraint forces. Okay, so we have a reaction force that's going to come from the hinge here. There's an equal and opposite force pressing on the hinge itself. And then these forces act, I say, to respect the hinge in the sense that whatever you're trying to do to this, reaction forces will be produced that are holding on to this to keep this thing from flying apart. So that's respecting the hinge. The gravity and reaction forces largely cancel. You get a small force and a moment, but still the reaction forces are going to scale linearly with muscle forces. So we said that the acceleration scales linearly with the torque that's applied or the force that's applied. And then the reaction forces are just going to be linearly related to those accelerations. And so that means that the constraint forces or reaction forces are also linear in your applied forces. And therefore, the same thing that you do with accelerations, you can do with reaction forces. You can break down what happens from an individual muscle, say, to get a muscle-induced reaction force. Okay, here's some details, which we're going to skip, but they're there for reference. Okay, so let's do another exercise. What I have here is something like, well, let me stand this way. I have a hinge joint, and then let's say I have another joint. And I'm going to apply a torque, basically pretend I'm applying a torque on my shoulder this way. That's what this arrow means. And then the question is, we already did this part, the first part. If I'm applying a torque this way, I think you know what's going to happen to this segment. But our question really is what's going to happen to the next segment. Okay, so again, the question is, what rotations do you expect from the two bodies? What do you expect at the end point? And maybe, what do I mean by end point? Let's talk about two endpoints. There's the endpoint of the first body, and then there's the endpoint of the second body. And then also, what do you expect in terms of reaction forces? So again, if you can talk to your neighbor for a minute, just see whether you can agree on what's going to happen in this system if we are applying our upward torque on the proximal end. Okay, that's the rotation. How about the translation of that point?
Are these equal moment of inertia, these two?
Sure,
Okay.
sure.
We predict this endpoint to go down.
Okay, great. Okay, let's take a look at our answers. There's the torque we're applying. I saw people drawing rotations. This rotates this way, and this rotates this way. Why do you think this one rotates this way? It's because you're going to have a reaction force acting on this joint, which is actually going to cause that rotation this way. So here's the translation of this body's center of mass. There you have a rotation this way. You're going to have a translation of the endpoint this way. This point is shared with this point. So whatever motion you see here, you have to have the same motion here. So you'll have a similar velocity. And then we didn't draw it, but there's a reaction force that produces that velocity. It's a reaction force that's going this way from this joint. And just like we said before, what could happen from that is you're going to get a rotation, and then this point can actually move in the opposite direction. So I am trying to lift my arm with my, say, my deltoid muscle, and then the induced acceleration is actually opposite to that. And so does that mean we should not use our deltoid to lift our arm? Who says yes? Oh wait, that was a confusing question. No, I have to ask this in double negative form. Should we not use our deltoid if we want to lift our arm? Sorry? Ah, well, good point. And hence part of the problem. But let's say we wanted to lift our hand. Should we avoid using the deltoid? Okay, I see some shaking of the head in the negative direction. Okay, anyways, the takeaway. Multi-body systems induce multiple constraint forces. Not all points accelerate in the same direction. The constraint forces and the accelerations are all, maybe it's too much to say that they're intuitive, but they're sensible. With a few minutes and just in thinking in terms of simple systems, you can usually pretty much figure out at least the direction that things happen. And then we're not concerned with the details of the actual numbers, but you could do that with knowledge of the masses and things like that. Okay, so this is what we discovered, something like this. And now I'm just going to switch up the problem a little bit, which is, again, we have an arm, but now I'm going to put a ground or some sort of a constraint there. And maybe I'll use this as my prop. Now the problem is I have my shoulder, I have my arm, and what I want to do is I want to press upward on this. Am I jiggling the camera? Okay, so that one doesn't matter. Okay, I'm pressing upward. The goal is to press upward with my hand. And then again, the idea is that the reaction force here, just like the, say, acceleration of the endpoint, both of these are just a linear combination of what you do with the muscles. And so a similar effect happens. Okay, any acceleration or reaction force of interest is linearly related to your active or your muscle forces. Okay, here's the puzzle. Let's add additional segments. So I'm going to add a segment. And then, of course, everything flips. So if we were using this example here, and I were to, say, apply my deltoid, then we expected my elbow to go this way. But then now if you include the hand here, then the hand is going to also receive an induced acceleration. And so if the wrist was going to move downward, the end of the hand moves upward. Oh, but I also have fingers. Okay, so maybe we should add the fingers on, and then the fingers are going to move downward. Oh, but a finger isn't a rigid body. Okay, so I have my PIP joint, so that's going to move upward, and then the DIP is going to move downward. And so, okay, I kind of lost track. I'm confused. I want to, let's say it's the tip of my finger, I want to move upwards. Now I'm really worried that the deltoid might end up making this move upward or downward, and then if I counted wrong, then I've got it all wrong. Okay, so we've got a problem here. To move the endpoint up, shouldn't we always move the proximal joint in that same direction? Or maybe I shouldn't say always, but just, just thinking sort of in terms of daily life, wouldn't you expect to use the proximal joint in that direction? And isn't that true regardless of how many joints? So most ways, I'm intentionally oversimplifying this, but the question is, I want to move the tip of my finger up, and most ways that I do this involve using my deltoid in that direction. Is that correct?
I would say the proximal joint should always rotate down.
Oh, okay. Yes, I should have added another segment to this so that it moves upward. Yes. So this.
I don't mean drawing. The sentence, I think, is wrong.
To move the endpoint up, shouldn't the proximal joint always rotate up?
Joint always should rotate down.
Oh, well.
But then the endpoint moves up.
Yes. Well, this is a rhetorical question, so in that sense, it's not wrong. But okay, but it is a serious rhetorical question, is that, I have my fingertip down here. I want to get up there. Most ways that I think of to do that involve using my deltoid and going this way. And of course, there are ways that I can move the fingertip up without using my deltoid. Okay. Here's the answer in a way. The answer is, first of all, accelerating isn't the same thing as moving, whatever moving means. We haven't really defined it. But, in everyday life, we think about moving our limbs, and we think about, I want to press upward with my fingertip. This is what we actually live with in daily life, I believe. And the answer is yes, in daily life, you do want to use the deltoid to lift your arm. But if you want to induce acceleration or force at the endpoint, the answer is technically no, or maybe I should say not necessarily, because it depends on how many segments we're going to include. And then, if I sprained my finger and I have a splint on one of the joints, then it reverses the sign of the effect of the induced acceleration. And then does that mean that you have to reprogram everything about what your central nervous system does to produce movement because you had a sign flip in your dynamics? So everyday life makes sense. Induced accelerations, I wouldn't say don't make sense, but you could be led to kind of silly conclusions like don't use your deltoids to lift your arm. Okay, so that's what I meant by the induced part. The intuitive induced accelerations part is we talked about how we have forces that are just going to produce rotation and translation, and then that ultimately led to accelerations and induced reaction forces, all of which I would say can make sense. There's no mystery here. Okay, so I promised we would talk about a couple things, so we'll do a case study of pedaling next. And so let's do a super simple model of pedaling, and let's try to understand what the hips effect is on the force you impose on the pedal. Okay, so we have a thigh, we have a shank and a foot, and then we have a pedal. And our goal is to perform positive work on the pedal. And the question is, which direction should we apply hip torque? Any opinions on that? Hip extension versus flexion. Who favors hip extension? Who favors hip flexion? Okay, so we have approximately equal numbers, I would say. Now, and I sort of intentionally didn't define this problem all that well, but I think that's part of the problem with induced acceleration analysis. Okay, so let's break this down. Here's our free body diagram. If I apply hip extension, that's going to cause a reaction force, a constraint force that's going to act downward on the knee. And then that's going to cause a downward reaction force on the ankle. And then we've already been through this. We have a body. We're going to whack it with a force acting downward on this end. So we already know what's going to happen here. It's going to cause a rotation like that. And then it's actually going to induce an upward force on the pedal. So according to this, it's a terrible idea for you to extend your hip if you want to apply force to the downward force to the pedal. Now, here's what we do know about cycling, which is that in this configuration, if you apply hip extension torque and the things are rotating in the direction that you would like, that the hip does perform positive work. Everyone knows that the hip performs work during pedaling, but it induces an upward force on the pedal, and it causes the ankle to flex or dorsiflex. One part is good, and the other part is bad. So here's a paradox. Hip extension is obviously desirable, but doesn't it press on the pedal in the wrong direction? Okay, when I say solution one, that's, I don't mean that's the answer to the question. It's more like that's one way to do this. And solution one is the muscle-induced acceleration way to do this. Okay, here's another view. Of course, we could flex the hip, which is going to perform negative work, but it will at least apply a downward pedal reaction force. So shouldn't that make us happy? So this is good, but now we're no longer happy because now the hip is performing negative work. It's actually taking energy away from our system. George Chen wrote a short article about this, and this is his main complaint, was just that this is a paradoxical or something that doesn't make sense about the analysis. And of course, there's a well-known solution to this, which is that you could just fuse this joint, and now it doesn't exist, just like how you could have a splint on the finger. And then once you fuse the joint, then you can put everything together, and then it makes sense. You do want to extend the hip, and that will induce a downward pedal force. But his complaint was that that's a subjective decision on what you consider to be a joint or not a joint. And you would rather have, you would prefer your model to be relatively insensitive to decisions like this, because I can fuse this joint, but then what if I have another joint there? Say I have an MTP joint for my foot, then we have the problem again. Or also, no bone is perfectly rigid. Every bone secretly is deformable. And so one model of a bone is to include a little bit of flexibility in it, such as a degree of freedom for to bend a little bit. And then that is going to reverse the direction of the pedal reaction force. Each of these decisions has an extreme effect on the direction of your induced reaction force. Okay. Andy Rina and Knut van Soest also gave a talk at the 2002 World Congress of Biomechanics, basically talking about how you have these problems. And then I think I have okay, so one of the examples they gave is that if you can move the pedal or move the attachment between foot and pedal a small amount, you can also induce flipping of the pedal reaction force. And so if you just move the pedal a little bit, you might go from producing a positive reaction force or positive force on the pedal or upwards to a downward force. And so they just pointed out that that's silly. Of course, you have a preferred place you want to press on the pedal with your foot, but it's not like things change drastically if you had the cleat located just a couple centimeters forward or backward. You might be annoyed, but it's not like suddenly your muscle coordination has to reverse. Okay, question?
Andy Rooney asked a question, so I can allow him to talk. So you can talk if you unmute your mic.
Oh, yeah. Actually, the thing we did was move the ankle joint a little bit. You only have to move the ankle.
Move the ankle joint.
Not move the pedal.
Thank you, Andy, for that entirely useless clarification.
Well, you only have to move the ankle joint a third of the length of the foot, whereas you have to move the pedal all the way pretty far to change the sign. And the ankle joint already.
Thank you for your additional useless factoid. Okay, so of course, another component to pedaling, if you had an ankle, is you can apply ankle extension torque. And ankle extension torque actually does what you want, sort of. By rotating the foot this way, of course, you get a force applied to the pedal that's in the downward direction. That's great, we're happy. There's a slightly unhappy part, which is that rotating the foot this way also induces a reaction force in the upward direction on your poor thigh. So your thigh is suffering now, it's going the wrong direction due to this force. So we applied downward force on the pedal, good, but we induced flexion of the hip or movement of the thigh upwards, and that's bad. Okay, so maybe we're belaboring this, but the point is that these arrows here are the result of all of this. These arrows are not incorrect. It's just that if you look at the arrows and you thought of each muscle on its own, you could draw all sorts of crazy conclusions that don't necessarily help you in understanding what's happening. And of course, I think everyone knows the answer, right? To pedal, you want to extend your hip. You want to, in this configuration, you want to apply extensor torque about the knee, plantar flexor torque about the ankle. The sum of all of those effects together gives you the downward force on the pedal. And then you sort of know that without doing a whole lot of analysis. Uh-oh. Okay, so Andy, you can correct me if this is wrong, but I'm paraphrasing you. Just don't think this way. Ton van der Bogaert also had a take on this, and his take was on most movements in life, not all, but in most movements, the inertial effects are really tiny. So it's true you have these sign flips of the induced reaction force or the induced acceleration, but these effects are tiny, tiny. And so especially in pedaling, quite often it's not like the accelerations are that enormous where you would have a sizable force due to these inertial effects. Or another way of saying it is, if you could replace your foot with a body that's basically the same as your foot in every way, except it has zero mass, that doesn't mean everything would blow up. You would actually be, as a cyclist, you might be somewhat happier to have that, but it's not like suddenly everything goes wrong. Okay, so Maybe I'll go quickly through this, but this is the way I like to draw pictures. And actually, there are pictures like this in my PhD thesis. I like to draw the effects as a diagram where you have, say, ankle extension and ankle flexion acceleration in one axis, and then upward or downward force on the pedal on another axis. And then I like to draw the effect of the hip torque, which is both to produce the upward force on the pedal, which we didn't like, but also to cause ankle flexion. And then if you include the ankle torque, it produces ankle extension and pedal downward. And the idea is that these two things add together to produce the resultant of producing downward force on the pedal, which is what we desired. So in this configuration of pedaling, you generally want to produce a downward reaction, a downward force on the pedal, and you want, say, relatively small acceleration, angular acceleration of the ankle. And we need not fret that these two arrows might be, in some ways, go the wrong direction, right? So the green arrow is going in the wrong direction of pedal force, but that's no big deal when you look at these arrows. These two things add up to this. And so one problem that we have is this idea that downward force good, upward force bad. I don't think people said that explicitly, but I think that that has been implied in the analyses. All we care about is that you have some muscles that allow you to produce forces and accelerations of different combinations, and you add those together to produce the resultant. Also, I should say, as biomechanists, even what this value should be, we are not very good at having an opinion on. So what I mean is, during pedaling, we can measure what people do, and we can say, here's what they normally do, a combination of pedal downward and ankle extension. However, so that's using the data and just looking at the data and say, that doesn't look too bad. We're not so great at each instant of time of saying what the goal is. So basically, we can't do any better than look at what people do normally and say, this is what you should do. Or maybe I should put it another way. Biomechanists can't give you a particularly good opinion on how to improve upon this. Okay, so anyways, we got good and good because you used the hip and the ankle together. This is what I call a multivariate approach, because we're trying to look at multiple outcomes at the same time, and just acknowledge that any single outcome might look terrible, but if you look at the aggregate outcome from aggregate of muscles, it is not terrible. Okay, so just a summary on how to pedal a bike. Extend the hip, extend the ankle, add those things together, you'll get a multivariate effect. And I would also say the lesson is, let's try to avoid univariate interpretations, because that's where the craziness comes from. The tibialis anterior accelerates the body downward during gait. That's a univariate interpretation. Okay, and then watch out for model dependencies where just by deciding whether a joint exists or not, you have a sign flip. If you do have that, maybe you're asking the wrong question. Okay, so that was our case study of pedaling. Let's do a quick case study of throwing a ball. And let's pretend that we have two segments here. We want to put a ball at the end and we want to throw it. And this, by the way, is meant to be an example where induced accelerations can be useful. So I'm not saying that induced accelerations should be thrown away, but I think it's just a matter of using them in the right way. So we have a ball. We want to throw the ball in that direction. We probably want to induce or cause velocities as shown there. And so should we produce torque to perform positive work and add energy. And here's an argument why you might want to do that. If you perform positive work, then you're adding energy to the system, and that means you can add energy to the ball. You want the ball to have kinetic energy. We can break this apart. Here's our free body diagram, and we're just going to give the solution here. We do want to apply a torque in this direction for the shoulder. That induces a reaction force on the other segment. And then, of course, we've already gone through this. If you were to apply a torque here alone, then you're actually going to produce the wrong direction of acceleration for the ball. So that sounds like a bad idea. So according to that, positive work is a bad idea. It doesn't help the ball move in the direction that we want. Here's another strategy, which you could call braking. Let's say you already had velocities like this, and then it makes sense for you to accelerate the ball with a torque in the opposite direction. And then we can do the same thing. And then what we'll end up with is applying a torque here accelerates the ball forward. Okay, so this sounds a little bit confusing. When you throw a ball, I think most people expect that they're going to apply torque in the forward direction. And I think that is mostly true. However, this is also a good idea. When is this a good idea? Near the end of the throw. At the end of the throw, it's a good idea to essentially brake your upper arm, because indeed it will, and we said the inertial effects are actually quite small, but you will get a little bit out of that, and that's a good idea. So you'll actually apply some more force on the ball in the direction that you like. But the reason why this is not a good recipe for the entire throw is because this also does some bad things, right? So it is going to slow down your upper arm. And so you can only do this. I think I have something that pops up here, but you can do this. You get extra acceleration, but you are doing negative work. And so if you did this for long enough, you would be taking a substantial amount of energy away from your system. And then that's going to cause all sorts of problems. And really what I want to say is the time to do this reversal strategy is at the very end, because the ball's going to leave your hand, and so you don't suffer any of the bad consequences of this negative work that you're doing on the system. Okay? So braking works, but it's a fleeting strategy. And that's also a lesson I would say about induced accelerations, is that induced accelerations is a snapshot in time, and it doesn't easily take into account the consequences after that snapshot. So at the end of your throw, we take a snapshot. Yes, if you were to brake or slow down your upper arm, that's actually going to help your ball move forward. But the same thing is actually true early in the throw, where we know it's a good idea to move your upper arm in the forward direction. And so the problem is the snapshot doesn't differentiate between those cases, beginning of the throw versus end of throw. Okay, so just to summarize, yes, you should flex your shoulder and you want to add energy. And then even though by induced accelerations that might make you think that you decelerate the ball, that's not necessarily a bad thing. And then you do want to reduce the energy at the end by slowing the shoulder, because that will at least give you a fleeting acceleration of the ball. Okay, let me move on from that. Okay, so we looked at throwing a ball. By the way, I apologize, we're taking some extra time. The tutorial that I gave was an hour time slot, and I know the HPL seminar is usually shorter than an hour, so I have to apologize for going a little bit long. But we did pedaling and throwing a ball. And the gait study I'm actually going to do super quickly so that we can get out of here. And I'm actually going to skip one part. And I want to move to another part, which is just to point out a kind of analysis that people don't normally do. Okay, I'm skipping all of this. Okay, let's think about the trunk, and let's think about what happens when your foot hits the ground with each step. And the idea is that you're going to have a ground reaction force at the bottom of the foot. That's going to be transmitted through the leg, and so you have ground reaction force acting at the bottom of the trunk, and then that's going to cause the trunk to pitch forward. Here's something else that happens. So it slows down the center of mass, and it's also going to redirect the center of mass's velocity in an upward direction. But here's something else that happens. Is that, remember that we received an impulse acting in this direction, and that is also going to affect the swing leg, and then that is going to cause the swing leg to, well, I don't know why I'm missing the other arrow, but one arrow should show that this is going to induce the thigh to rotate in the forward direction, and then it's going to rotate, it's going to induce the shank to move in the opposite direction. In other words, this is going to induce the swing phase of gait. Now, in typical biomechanical gait analysis, the argument that people have is what initiates the swing phase, and the typical argument is it's the ankle plantar flexion of the trailing leg that initiates it, or some people say it's the knee or the hip of the trailing leg, or some combination thereof. And then an analysis that people don't normally do is the idea that just the foot hitting the ground and you keeping your leading leg straight is also a way to initiate the swing leg. And then you don't need any torques about the hip, knee, or ankle of the incoming swing leg. And so this is an example where induced acceleration analysis of a sort, it's a different kind, but still the idea is that you induce reaction forces, you induce accelerations, and then that can lead to good understanding. Okay, so we did pedaling, throwing, and then we talked about gait for a few seconds. Let me just do a little discussion. One of the problems that I would say is what I would call connotation. What is the goal of gait, and what is good or bad at each snapshot in time? And an example of a connotation that I think is not that helpful is we often talk about propulsion, and I think the connotation of propulsion is good, as in that's a goal of gait, is you want propulsion. And then another term that we use is braking, and I believe the connotation to that is bad. And I think that's problematic. Also, there's body weight support, and the connotation to that, I believe, is that upward body weight support is good. Falling in the opposite direction is bad. And then here are the muscles that are associated with those things using muscle-induced acceleration analysis. So then the vasti and the soleus contribute to braking, the gastrocnemius contributes to propulsion, and then this sounds like we are gaining understanding, but I'm not sure what to do with this information. What if you want someone to walk faster? One idea might be, if this is braking and slowing you down, then maybe what you should do is you should apply Botox to all the bad muscles, these and these, and then the person will stand up straighter, I'm not sure. Maybe they'll walk faster or they'll get more propulsion. And I don't think, I'm being facetious here, I don't think any serious person believes that's a good idea, but that's what I mean by there's a problem with connotation. Why do we need the terms propulsion and braking if they don't tell us what to do? They sound like a description, but I would say it's a little bit of a misleading description. Also, just to remind ourselves, walking on level ground at a steady gait over one period of gait or any integer number of periods involves zero net work, zero net acceleration, zero net vertical displacement. So walking at steady speed, in a way, your net propulsion, the goal is zero. It's true, if you're starting from still and then you start walking, there is a period of time when you want positive forward acceleration of the body. But once you're steadily walking, you no longer have a goal of propulsion, or at least not net propulsion. Okay, so you want equal propulsion and braking, and so you might be careful about connotations. Okay, so what's my recommendation? I think these are misleading or maybe misdirecting connotations. They imply goals that we don't have in walking. So if that's not the goal, let's not use terms that sound like they are goals. Here's a shipping analogy. Oh, I meant this to be, don't look at the right, only look at the left because this sort of ruins the whole story. I want to ship a package from Ann Arbor, Michigan to Calgary. I'm going to do analysis called plane-induced transport analysis. The observation is that I see a Boeing 777 used in one segment, then a 757, then an Airbus 310. And from that analysis, I discovered that the 777 always goes in the wrong direction. It's in the negative direction of going towards Calgary. The 757 also goes in the negative direction, and the A310 goes in the positive direction. This is true information from my analysis. But what are we going to do with that information? Does that mean we should acquire more A310s or install bigger engines? Maybe we should reduce the number of 757s, 777s, or maybe we should put brakes on them or smaller engines or something. Okay, here's another analysis. Here's just a map. Here's Ann Arbor. Here's Memphis, which is a FedEx hub. And here's Toronto, which is another FedEx hub. And then what's happening is everything in the US gets shipped to one of the major hubs, usually Memphis, even if it goes in the wrong direction. And then if you want to get to Canada, many, many things go between the two hubs, Memphis to Toronto. And then finally, you get your flight from Toronto to Calgary. If we look at any of these individual pieces of information, this is tantalizing information. You know, if I'm tracking my package, I might say, well, I want a refund. You're spending fuel to go in the wrong direction. Stop doing that. But if you look at the map, it makes sense. If you understand why they have hubs, it all makes sense. This is plane-induced transport analysis. It's not necessarily incorrect. All of the facts I've told you are correct, but they can be confusing or misdirecting. And I would say plane-induced transport analysis is kind of a PITA. I won't translate that. Okay, I showed this diagram before of pedals and ankles. The idea is that these arrows are the same things as the shipping routes. And so we need not fret when the FedEx plane goes in the quote wrong direction. It may actually still get you the package in the end. Okay, just to summarize, I said there's a connotation problem, there's a model dependency problem, and then there's a problem with the snapshot analysis that doesn't take into account what happens over time. I would also say that what we're doing here is a lot of interpretation. And I think interpretation should not be the goal of what we do. Interpretation is something happens and we look at it after the fact. What we'd really like to do is we'd like to make predictions and test them. And then in a way you don't need terms like propulsion and braking. You just need a prediction of what's going to happen. And you don't need to attach a term to it that sounds like it's a goal. Because if we can predict what happens, we can make things happen. Here is an example of people who make things happen. This is Atlas by Boston Dynamics. And Atlas can do things like this. I don't know, I don't have the video here, but they also do a backflip off of a box. And the point is that Boston Dynamics is doing everything that biomechanists would like to be able to do. They are able to devise a control for the robot to do what they want. They can design the robot. They can make it do everything. And here's how they do it. They use a lot of optimization and a lot of common sense. What do I mean by optimization? To get the robot to do what it does, they minimize the cost function, which includes lots of things that matter to them. And then they're choosing a feedback and a bunch of control parameters that are going to execute that task. Subject to dynamics. What I mean by dynamics is they do use the mass matrix and the equations that we showed at the beginning. They also take into account actuator limits and task requirements. But perhaps most importantly, no muscle-induced acceleration analysis is used in order to do this. If you talk to them, they are fully aware of inertial effects, but that's not what they're worried about on a day-to-day basis. They also don't use terms like propulsion, braking, or body weight support, and they can do everything. And so that's just an argument that maybe we don't need to do that. Okay, so I'm just giving a final summary. We want to recognize model dependencies. We want to avoid connotations. And we want to study movement over time, not as a snapshot, for example, using optimization. And then we want to perform more and better experimental tests where we're actually testing predictions. I want to just close with my some acknowledgments. The Benno Nig Research Chair, which made this possible, NSERC, and other sources. So thanks for sticking with us.
I'd like to start.
She's got her hands up.
Oh, sorry, yeah.
The diagram of this?
I think what many of the biomechanists would say out of that is, oh, yeah, even though combination of them are doing the job, it might be a good idea to not have the book, instead is reducing the pattern down. So just to clarify, I do think that we cannot really do that because those things are somehow coupled.
Okay, so the question is, just to repeat the question, if anyone's listening to the stream, some biomechanists might say it could be a good idea to get rid of the hip torque. And then what am I exactly saying about that? Well, one question is, given what you have, how are you going to use that to do something? And then you could say a larger or a different question is, what should you have? So what I mean by given what you have is you have muscles in your body in a certain configuration. And today you have no choice on adding muscles or substituting others. And so you just have a bunch of arrows in different directions. And then you're going to compose those arrows in some combination to produce the task. And what I'm saying is this is imposed on you, these exist, and then the fact that you add them together, that is your decision. But there's nothing about this that says that this muscle is a bad idea or using this muscle is a bad idea. the other question is the design question of what would you like to have. And I would agree that if you could delete these two muscles and replace them with a special muscle that goes only in this direction, that might help out. But even then, well, first of all, that's for a snapshot, so there may be consequences later in time that you don't like. And then there are various practicalities of deleting muscles and adding them. But if you talk about what is the control problem for most people, the problem is, given muscles, what should you do now and over time? And then the design problem, if you are designing new beings, is how should you arrange these muscles? And again, I think in these terms all the time. So in that sense, I'm a believer in induced acceleration analysis. I just don't like making interpretations like, oh, the hip torque is going in the wrong direction. I don't find that helpful.
Maybe just to add to that, you know, I think it's one way to think about the muscles and how they all work. But you know, you can think about pedaling, for example, also kinematically, you know, and if that pedal is there and I want to push it down, I have to extend the leg. If you assume that you don't use the hip at all, and the hip would be fixed, you know, that pedal is never going to go down. So, you know, it's kind of like I have this here and I have my arm here. I didn't want it to go there. I mean, there's various ways I can do it, but somehow I have to extend my arm and somehow I have to extend my leg. Otherwise, that pedal is not going to go down, independent of really exactly how you use the muscle. I've got a panelist that would like to talk. You're allowed to talk. You just need to unmute your microphone.
Hi, Art. Can you again just in summary state when induced acceleration analysis is useful and when it's not? Is it only useful for instantaneous analysis where there's only one actuator at work?
I think that's a little bit unfair to say. It is a snapshot analysis, and so I don't have an opinion of it's only good for snapshot or not. I actually, when I think about movement, I'm always thinking in terms of things like this, diagrams like this, where I'm thinking of the vectorial contributions of different things, and then I try to keep in my head that there are consequences later in time, and maybe there's a diagram for this for different instances all around the pedal cycle. And for me, it's helpful to know that and to think in terms of that. But I'm not interested in interpretations of this arrow goes in a certain direction and that arrow goes in another direction. Or to state it another way, Boston Dynamics makes heavy use of the mass matrix. All of the numbers in the mass matrix, I shouldn't say all, but most of the numbers are of interest to them. And then they like to have a good model of their robot, and more accurate is better as far as they're concerned. So in a sense, you could say they are obsessed with the individual entries of the mass matrix. However, they don't have meetings where they say, wow, look at this. This entry in the mass matrix is negative, and that means that things go in the wrong direction. They don't have discussions like that.
I agree largely with what you said, and also with this panel, but I have one problem with the panel, and that is that for cycling, I would say this panel is wholly unimportant because the direction of the force on the pedal does not matter. You're only interested in doing as much positive work as possible in order to overcome air friction. And for doing a lot of positive work, the direction of the force on the pedal has no meaning whatsoever. You're only interested in doing positive work with your muscles.
I think that's
yeah, so in that sense, I do have a problem with the panel.
Okay. Well, I would say what you're saying is a little bit in line with what Andy Ruina says, which is if you want to know what muscles are important, if you're doing positive work, maybe look at which muscles are doing positive work, and those are probably important. And then I would go a step further and say, if you want to know which muscles are important, why don't you look at which muscles are active during normal movement? And then that's going to give you a clue. And the reason why I even include muscles that might do negative work during a positive work task is because I do not have the expertise to say that this muscle, which is active and doing negative work during pedaling, should be Botoxed or should be dissected and removed. If it's used in normal movement, I don't think as biomechanists, we are that good at saying it's a bad idea. Or another way of saying it, this panel here only has 2 degrees of freedom. And in the body, you have an unknown number of degrees of freedom of things that you could vary which might matter to you. Like, what if pedaling a certain way causes pain in your patella? That's another axis. Or what if pedaling in this way, if you do it long enough, makes your neck sore? Who knows? So one thing that is a little bit hopeless for us is to know all of the sort of variables that matter to the person and to faithfully record them in a panel like this.
Time for one more question. Probably just a comment to that. You know, pedaling is a good example because Francisca, she looked a little bit at that, and then you're in certain phases of the power phase, let's say very high up at a 30-degree or 40-degree angle. Then if you want to exert force in the direction perpendicular pedal, you're actually extremely weak. You cannot really do very much. However, if you just essentially think about extending your leg and you're very strong, then in that other direction, the tangential component will become very big. So there's also considerations of what your muscles can do and how strong they are, and in what direction you want to push, because how much force you have available for that is a very, very strongly direction dependent. The other thing I thought about cycling was interesting that you said when you cycle, think about hip extension and ankle plantar flexion. When I cycle, I get tired, my thigh muscles get tired, my quadriceps muscles. So what about the knee joint?
I'm a big believer in the knee joint.
Oh, good. Because that's where I get tired.
Oh, I see. For this diagram, yes. Yes. If I could, I would draw this in many different dimensions at once. And I completely agree. The knee, or it's the quadriceps muscles that get massive in cyclists more than anything else. And so I would agree that that's probably an important muscle during cycling. Thanks for bringing up the point about the pedaling, because as far as I'm concerned, these are all similar kinds of things where people have sometimes overinterpreted things. And one of them is the project you're talking about, where for decades there have been some people who have been concerned that you apply forces in the wrong direction of pedaling, meaning not only in the tangential direction. And then there have been people who've gotten really excited about biarticular muscles because they do something super special. And I do think biarticular muscles are a great idea, but in a way, there's nothing special about them. And this kind of analysis with the vectors, I find very helpful in illustrating why, yes, biarticular muscles are a good idea, but so are all other muscles.
Awesome. Well, I'd like to personally thank Art for sitting my behind and presenting this week. And let's thank him one more time for Scott.
All right, next week, our presenter will be Dr. Kati Passanen, who will talk on prevention of lower extremity injuries in youth team sports. See you next week.